In the previous videos, we explored the Hazen-Williams formula for determining pressure loss in pipes. The Darcy-Weisbach equation is another important method, and according to NFPA 13, it must be used for anti-freeze systems exceeding 40 gallons in volume. NFPA 11 also requires the use of this equation to calculate friction losses in piping that carries foam concentrate. Although the Darcy-Weisbach equation is more accurate than Hazen-Williams, it is also more complex to apply. In this video, we will become familiar with the Darcy-Weisbach equation and learn how to use it effectively. In academic textbooks, the Darcy-Weisbach equation calculates head loss in feet using the format shown on the screen. In this equation, F is the dimensionless friction factor, L is the pipe length, and D is the inside diameter, both measured in feet. V represents the fluid velocity in feet per second, and G is the acceleration due to gravity in feet per second squared. The most challenging part of applying this equation is finding the friction factor. It depends entirely on the flow regime. In general, fluid flow in pipes can be categorized into three conditions: laminar, transitional, and turbulent. In laminar flow, the fluid flows in perfectly straight parallel layers that just slide smoothly past one another. There is no mixing or swirling. In transitional flow, the straight layers start to break down and little ripples or swirls begin to form, but it isn't completely rough yet. Finally, in turbulent flow, the fluid is swirling, mixing, crashing into the pipe walls, and completely chaotic. The smooth layers are completely destroyed. As the flow changes from laminar to turbulent, the head loss increases significantly. To determine the flow regime, we use a parameter called the Reynolds number. It is calculated by multiplying the fluid's density, velocity, and the pipe's inside diameter, and then dividing that result by the dynamic viscosity. Dynamic viscosity is a measurement of the internal friction within a fluid. To understand this intuitively, imagine stirring honey. The resistance we feel against the spoon is a direct result of the honey's high dynamic viscosity. We can also calculate the Reynolds number using kinematic viscosity. This parameter describes how a fluid flows under its own weight and the force of gravity. To visualize this, imagine tilting a jar of honey. Because honey has a high kinematic viscosity, it pours very slowly. Kinematic viscosity is calculated by dividing the dynamic viscosity by the fluid's density. Therefore, if we use kinematic viscosity, the formula for the Reynolds number becomes simpler. We just multiply the fluid's velocity by the pipe diameter and divide by the kinematic viscosity. Now that we know how to calculate the Reynolds number, let's look at how it relates to the flow condition. It is important to note that the specific Reynolds number ranges for each flow regime can vary slightly depending on the textbook. However, in general, when the Reynolds number is less than 2,300, the flow is considered laminar. For a Reynolds number between 2,300 and 4,000, the flow is in the transitional phase. Finally, if the Reynolds number is greater than 4,000, the flow becomes turbulent. To calculate the friction factor, a key parameter in the Darcy-Weisbach equation, we first need to determine the flow condition by calculating the Reynolds number. Once we have that for laminar flow, the friction factor can be calculated simply by dividing 64 by the Reynolds number. If a flow falls into the transitional regime, the water is highly unstable, constantly flipping between smooth and chaotic flow. Because of this unpredictability, there is no reliable equation to calculate the exact friction factor in this zone. Finally, for turbulent flow, there are generally three methods to determine the friction factor: the Moody diagram, the Colebrook-White, and the Swamee-Jain equation. Let's start with the Moody diagram. In this diagram, there are three axes. On the bottom horizontal axis, we have the Reynolds number. This represents our flow condition. It starts with slower flow on the left and moves into highly chaotic, turbulent flow on the right. On the right vertical axis, we have the relative roughness, shown as epsilon over the inside diameter of the pipe. Epsilon tells us how bumpy the inside of the pipe is, and its value can be found in standard engineering tables. Lower numbers mean a smooth pipe, while higher numbers mean a rough pipe. For each epsilon over d ratio, there is a corresponding curve on the graph. If we calculate a value and there is no exact curve printed for it, we can simply use interpolation to estimate where that curve would be. Finally, on the left vertical axis, we have our destination, the friction factor. To find the friction factor, we just follow 3 steps. First, we find the pipe's relative roughness on the right axis and follow its corresponding curved line into the graph. Second, find our calculated Reynolds number on the bottom axis and move straight up until you intersect the curve we are tracing. Third, from that exact point of intersection, move straight across to the left axis. The number we land on is our friction factor, ready to be plugged straight into the Darcy-Weisbach equation. While the Moody diagram provides a highly effective graphical method for determining the friction factor, computational applications require a distinctly different approach. When developing spreadsheets or specialized hydraulic calculation software, we cannot rely on graphical analysis. Instead, we require precise mathematical formulas. This requirement brings us to the Colebrook-White equation. Developed in the late 1930s, this formula is widely recognized as the foundational standard, effectively serving as the mathematical basis for the turbulent flow region of the Moody diagram. However, applying this equation presents a significant mathematical challenge. Upon examination, it becomes evident that the friction factor is present on both sides of the equation. In mathematics, this is classified as an implicit equation. Because the equation is implicit, it cannot be solved algebraically for f in a single direct step. Instead, it requires an iterative process. We must estimate an initial starting value, perform the calculation, assess the error, and repeat the procedure until the mathematical solution converges. While computers and hydraulic software are exceptionally well suited for this type of iterative computation, performing these calculations manually is highly inefficient and time-consuming. To resolve this limitation, the Swamee-Jain equation was introduced in 1976, providing a highly practical alternative. The Swamee-Jain formula is an explicit equation, meaning the friction factor is isolated entirely on one side. By utilizing the specific pipe roughness and the Reynolds number, we can compute the friction factor directly in a single, straightforward calculation. Although the Swamee-Jain equation is technically an analytical approximation of the Colebrook-White formula, it offers exceptional accuracy, typically yielding results within a 1% margin of error. It's important to note that the Swamee-Jain equation is valid for fully turbulent flow. In this region, the friction factor depends solely on the relative pipe roughness and is completely independent of the Reynolds number. If we look at a Moody diagram, we'll see this represented as a straight horizontal line. For very smooth pipes, such as CPVC or copper, the relative roughness is extremely small. Because this can push the limits of the Swamee-Jain approximation and lead to less accurate values, it is better to use the Moody diagram or the Colebrook-White equation for maximum precision. While the classic format is great for textbooks, in fire protection engineering, we need an equation that speaks our language. The version we'll actually use in the field looks like this. This modified format is designed to align perfectly with the parameters we use in the Hazen-Williams formula. Instead of calculating head loss in feet, this formula gives us the friction loss directly in pounds per square inch. Rather than figuring out fluid velocity in feet per second, it lets us plug in the flow rate directly in gallons per minute. And instead of measuring pipe diameter in feet like the classic format, we get to use the inside diameter in inches, which is exactly how we size pipes in the real world. We might also notice that the gravity variable from the classic equation is missing. That's because, at least for now, we are still designing water-based fire protection systems here on Earth, not on the Moon or Mars. Since gravity is a known constant, it has simply been baked right into the math. All of those unit conversions, shifting from feet to inches, converting flow to GPM, and substituting gravity with its Earth value, have been rolled up into this single number at the front, 0.000216. The Reynolds number can also be rewritten in a form that aligns with the typical parameters and units used in fire protection systems. In these versions of the equation, we use units common in fire protection: flow rate in gallons per minute, density in pounds per cubic foot, pipe diameter in inches, dynamic viscosity in centipoise, and kinematic viscosity in centistokes. When applying the Darcy-Weisbach equation for fire protection systems, the specific roughness value or epsilon factor of the pipe material can be obtained from Annex A of NFPA 13. Table A282482 provides suggested epsilon factors for various pipe materials such as steel, copper, and plastic, alongside their corresponding Hazen-Williams C factors. As previously discussed, the epsilon factor is used to determine the friction factor. As we discussed earlier in this video, fluid flow inside pipes can fall into three regimes: laminar, transitional, or turbulent. Now the question is, which one actually occurs in fire sprinkler systems? To answer that, let's walk through an example and calculate the Reynolds number for typical sprinkler flows. Consider a 1-inch Schedule 40 steel pipe carrying 20 gallons per minute of water at 50 degrees Fahrenheit. For water, we'll use a density of 62.4 pounds per cubic foot and a dynamic viscosity of 1.3 centipoise. Substituting these values into the Reynolds number formula gives a result of about 46,300. This value is far above the threshold of 4,000, which marks the beginning of turbulent flow. Now let's cut the flow in half down to 10 gallons per minute. Repeating the calculation, the Reynolds number becomes 23,150, still well into the turbulent region. Finally, let's push the flow even lower. At 1.73 gallons per minute, the Reynolds number drops to about 4,006, which is just above the turbulent threshold. This is essentially the lowest flow that could still be considered turbulent in this pipe size. But here's the key point. Based on the K-factor table and the minimum operating pressures required by the standards, the actual minimum flow delivered by a sprinkler is higher than 1.73 gallons per minute. In real installations, sprinklers operate at flows that produce Reynolds numbers far above the zone where flow behavior begins to shift away from turbulence. So the conclusion is straightforward. The flow of water, without any additives, in fire sprinkler systems is always turbulent. This is why hydraulic calculations using the Darcy-Weisbach equation rely on friction factor values associated with turbulent flow. This part of the video examines an interesting paradox involving the friction factor and pressure loss, one that often leads to confusion when engineers first study the Darcy-Weisbach equation. We all know that as we push more water through a pipe, meaning a higher flow in GPM, our pressure loss increases. We also know that increasing the flow rate leads to a higher Reynolds number. On the other hand, if we look at the Moody diagram, we see that for any given pipe, as the Reynolds number increases, the friction factor actually decreases. According to the Darcy-Weisbach equation, a lower friction factor should reduce the pressure loss. So, what's going on here? The key point is that the friction factor is not the primary driver of pressure loss. When we examine the Darcy-Weisbach equation, two opposing effects appear as flow increases. On one hand, increasing the flow rate causes the friction factor to decrease slightly. On the other hand, the pressure loss term is proportional to the square of the flow rate, and this relationship dominates the behavior of the equation. In practice, the modest reduction in friction factor is overwhelmed by the much larger quadratic growth of the flow term, and it's not a fair fight. The flow squared term always wins. As we have seen, the Darcy-Weisbach equation evaluates more variables when calculating friction loss. While the Hazen-Williams formula only considers the flow rate, pipe material, and inside pipe diameter, Darcy-Weisbach also incorporates critical fluid properties such as density and viscosity. Given that Darcy-Weisbach is more accurate than Hazen-Williams, a critical question arises. How significant is this added accuracy, and is it worth the complexity of using it when designing fire sprinkler systems? To answer this, let's run through a practical example. We'll calculate the friction loss for 20 gallons per minute flowing through a 1-inch Schedule 40 pipe at 68 degrees Fahrenheit. First, we pull the water's density and dynamic viscosity from thermodynamic tables at that specific temperature, which allows us to calculate our Reynolds number. Next, we determine the epsilon factor, which represents the internal roughness of the steel pipe in a wet sprinkler system. With the Reynolds number and the epsilon factor both in hand, we apply the Moody diagram to determine our friction factor. Finally, plugging it all into the Darcy-Weisbach equation gives us a precise pressure loss of 0.128 pounds per square inch. Because the pipe length in this example is 1 foot, the pressure loss is also 0.128 pounds per square inch per foot. Using the Hazen-Williams formula for the same pipe gives us a pressure loss of 0.130 pounds per square inch per foot. Comparing the results, there is only a 0.002 pounds per square inch per foot difference, which is truly negligible in fire sprinkler design. The Hazen-Williams formula is an empirical equation. It was built using experimental data specifically for water at standard temperatures. Because water's density and viscosity are already baked into the formula, as long as those properties don't change, the results are highly accurate. However, when the fluid changes, Hazen-Williams no longer works. This is why NFPA standards mandate equations like Darcy-Weisbach for systems using large volumes of antifreeze or foam concentrate, because we have to account for the new fluid's actual density and viscosity.